Okay, this is another little mini lecture to make up for some of the time we've lost in the semester so far. Chomsky and asteroids and whatnot. We're going to be talking about doing a couple of derivations for adiabatic processes. It's not the most exciting thing, but it's something that's very important, and this is why I didn't want to really waste class time for it. There's a couple of derivations that are a little involved, but are important because the results especially are terribly important. Now, first of all, an adiabatic process is, you should ask yourself, what is an adiabatic process? Hopefully you know. If not, pause and look it up. So if you know, then you know that it's a process where there is no heat exchange. So it's a perfectly insulated system. So our first law of thermodynamics, of course, says that the change in internal energy is heat plus work on the system. And if there is in fact no heat, if this goes away, Q goes to 0, then basically it's all about the work. So in an adiabatic process, the only change in energy is the work. And that's important because we can get a very, very precise relationship between pressure and volume in an adiabatic process. You remember in an isothermal process, where basically the internal energy is constant, we had the two related by the perfect gas law. Basically, P is inversely proportional to V. So as V goes up, P goes down in a proportional manner. The relationship between P and V in an adiabatic process is a little bit more complicated. So, by the way, ignore this for an ideal gas Q is equal to 3 halves. I don't know how this got here, but it's a problem with PowerPoint. At any rate, ignore that for the moment. We are going to be using that, but sooner than we get to that side of the page. So, anyway, for an adiabatic process, the heat goes to 0, and the change in internal energy is just the work. And that means if you have a tiny change in volume, the tiny change in internal energy is going to be equal to negative P dV. Okay, because that's how we get the total change in energy, is by integrating P dV. And the work on the gas would be negative P dV, because for an expansion, it's negative work on the gas, and for a compression, it is positive work on the gas. Okay, so we're going to take this equation here and divide both sides by dV. Okay, dV. And then the dV's go away on the right-hand side, and we are simply left with du dV is negative P. And we're going to draw a little circle around this, or a little oblong ellipse around it, and keep that in mind because we're going to come back to that a little bit later. In the meantime, we're going to get another expression for du dV by using the perfect gas law, or not really the perfect gas law, by using the definition of what internal energy is. From the kinetic theory, we found that internal energy is some constant times nkt. It is proportional to the kinetic energy of each of the little molecules. So that's why you have the n in there. And the kT is proportional to the amount of energy that each molecule has. And then the constant is how much you have with kT. We're going to use the letter Q for the constant. Okay, so internal energy is Q times nkt, which is also Q times PV, because we know from the perfect gas law that PV is equal to nkt. Okay, and this is where we get that little extraneous thing that we have on the right-hand side. For an ideal gas, this Q is 3 halves. Okay, we derive that with the molecules in the box, and we said that for an ideal gas, we find that Q is 3 halves. Okay, now let's say we want to take the differential of this. We want to do d dV of this whole thing. Okay. Well, we're going to do we're not going to worry about the nkt part. We're just going to do the differential of the Q times P times V. And since P and V are multiplying each other, we of course have to use the product rule. Okay. And so from the product rule, we go up here and we find du dv is qp times dv dv. Okay, first you take the differential of the v, and then you take the differential of p with v. So you add qv times dp dv. But of course, dv dv is like dx dx. It's just 1. So we can cancel that out. And we have du dv is q times p plus qv dp dv. All right, but that is du dv. Right? That is the differential of the internal energy with v. But look at this. We already have done that. We said over here, by using the first law, that the u dv is negative p. So which one is it? Well, it's both. And what we are going to end up with is a differential equation equating those two. Okay, so let's equate the two. We find du dv is both qp plus qv dp dv, and that's equal to negative p. Okay. So those two expressions are equal to each other. And then we can do some rearranging. So I'm going to go through that pretty quickly, and I'll let you try to follow along by stopping the video. Okay. We bring the qp on the other side and factor out the p. Okay. Then we solve for v, okay, by dividing both sides by q and multiplying both sides by dv dp. And then we flip everything to the other side again so that we make it equal to 0. And the reason we do that is because then we have a differential equation that is equal to 0. Okay. Now remember, we said that for an ideal gas, Q is equal to 3/2. So that means on the top of that term in parentheses, we have 2/2 plus 3/2, and on the bottom we have 3/2. So 2/2 plus 3/2 is 5/2, and on the bottom we have 3/2. So that means that Q is equal to 5/2 over 3/2, but that's also equal to gamma. Remember gamma? That was our ratio of Cp over Cv from a lecture or two ago. Okay, and Cp over Cv, remember, is always greater than 1 because the specific heat at constant pressure is always bigger than the specific heat at constant volume, because when you're doing it at constant pressure, the gas has to do work so it doesn't heat up as rapidly. Okay, so if we just put in gamma for this whole term here, so basically we're substituting gamma for 1 plus Q over Q, it just neatens up the equation a little bit, and we have gamma P dV dP plus V is equal to 0. Okay. This is a differential equation, and those of you who have differential equations might know how to solve it. But differential equations is not a prerequisite for this course, so I'm going to just tell you how to solve it, because frankly I'm not sure I would remember quite how to solve it either. But if you multiply this by v to the gamma minus 1 power, right? You have to kind of, that's the thing about differential equations, they're more an art than a science. You have to give things a try and see if they will work out. Well, if you multiply by v to the gamma minus 1, you come up with something that looks more complicated, right? It looks a little more complicated, but it's actually solvable. Okay, so basically this first term here, we've put a v to the gamma minus 1 in there, and this next term here, v, which is v to the 1 power, we just added, we end up with v to the gamma minus 1 plus 1, which is just v to the gamma. Well, it turns out that this thing here is true if this is true. Okay, the solution to that differential equation is d dp of P times V to the gamma equals 0. So in other words, the differential of this term here, this PV to the gamma, has to be equal to 0. And whenever you have a differential of something equal to 0, that means that it's constant. And there's our important result. The important result is that for adiabatic processes, P and V are related by this. It was a long way to go, but the payoff is worthwhile because it shows you that P and V are related in a special way. Just like in an isothermal process, you got PV proportional to temperature, and that's constant. In an adiabatic process, you have PV to the gamma, the constant. And so for an adiabatic process, you also have P is inversely proportional to V to the gamma power. Okay, so this tells you how P varies with changes in V, as long as no heat is allowed in or out of the system. If we were to draw this on a PV diagram, yes, it would look like a curve that is somewhat similar looking to an isothermal curve, but it's different. Okay, in an isothermal curve, you have P is proportional to 1 over V. In an adiabatic curve, you have it's proportional to 1 over V to the gamma. Okay. Now, the gamma is going to depend on whether you have an ideal gas or not, but we will get to that in a little while. Then the question becomes, what is this area under the curve? Is that doable? Well, of course it's doable because now we have P analytically as a function of V. So we know that P is not just a random thing, but similar to the way we know for an isothermal process what P is as a function of V, here we know what P is as a function of V. It's just a little bit more complicated. Okay, and so that's the next thing we're going to do. We're going to try to figure out what the work is for that adiabatic process. But since I'm coming close to my 15-minute time limit, I think I'm going to stop this video at the moment and continue that on the next one because I don't think 2.5 minutes is going to be enough.